So, good afternoon, all. I welcome all of you to the day two of our program, Optimization Techniques, Theory, Practice, and Emerging Applications. So, today, Professor Prakash sir is there. So, sir is going to discuss about different introductory part of the optimization techniques, as well as there will be some hands-on session with the MATLAB optimization toolbox. So it's my privilege to introduce Professor Prakash sir to the participants. So sir is currently working as an associate professor in the Department of Chemical Engineering at IIT Guwahati. Sir received PhD degree from IIT Bombay in 2008 and MTech degree from CIT Coimbatore and BTech degree from Pondicherry Engineering College, Pondicherry. So, sir's teaching and research interests are applied optimization and computational intelligence. Sir received several travel grants from DST and Dr. A.V. Ramarao Foundation's best PhD thesis also. Sir has awarded Research Award in the year of 2011 and PhD Student Excellence Award also sir received. So, sir is having a number of good number of research publications in various reputed international journals and conferences. Sir is also having a number of NPTEL video lectures related to various optimization techniques. So, with this brief introduction, I welcome once again Sir to our program and I request Sir to start his session. Over to you, Sir.
Thank you, madam. Just a couple of minutes. I just need to set something up here.
Okay, Sir. Okay.
So I hope the screen is visible, ma'am.
Yes, Sir, it is visible.
Okay, thank you. So I'm going to briefly talk about introduction to optimization. And in the first half, I'm also going to show you how we can handle constraints. After that, we'll go to that MATLAB hands-on session. So primarily, optimization are computationally intensive work. So we have broadly three different softwares which can be used to solve optimization problem. One which you all probably are familiar with is Optimization Toolbox. And then we have something called as IBM iLog Simplex Optimization Studio. So for those of you who are from academic background, involved in academic activities, this software is available free of cost, the full version. And then we have something called as GAMS. Right? So we'll see like there are different types of problem, and each of this software is suitable for a particular type of optimization problem. So I presume that you have had one day on optimization. Yesterday probably you had discussed some lectures. So I would believe that you know applications, but commonly cited applications are timetabling. When we do a scheduling of a timetabling, that's an optimization problem. If you want to select a site to establish an industry, that is an optimization problem. Production planning, controlling, and scheduling also involves optimization. And pretty much whatever you can think of, even the fact that you are attending this lecture is actually a decision of an optimization problem that you solved. You may not have solved it with pen and paper, but you did see that you want to attend this course, you want to maximize your knowledge, and what are the constraints that you have aligned to that, you would have chosen to attend this program. So pretty much what we do in our everyday life is a result of an optimization problem. So these slides will be made available to you. So this slides basically shows the use of those three softwares which we discussed among wide range of problems. So this is for GAMS. So here you can see the type of problems and the subject. So subject, if you can see, it spans a diverse area. So I'll not go into this in depth about this thing. Okay, so a common optimization problem that we come across is called as a traveling salesman problem. So in this problem, a salesperson wants to find the minimum cost route in an n city situation. So here there are five cities. The salesman wants to travel from all the 5 cities without necessarily repeating any city, and each city is to be visited exactly once. So the money required to travel from A to B might be different from B to C. So he or she wants to looking for an optimal path, like schedule which will take him or her to all the cities with the least amount of money. Again, this is a knapsack problem, a very common optimization problem. Here we have an hiker who wants to climb up the hill. So these are the different types of products which are available, and each one has its own values. Each one has its own value. So the hiker wants to decide which of these items should he or she take up the hill, given the constraint that he or she cannot carry above a particular weight. So that is knapsack problem. And then we have this map coloring problem. So in this map coloring problem, it's primarily a feasibility problem. So a feasibility problem is similar to an optimization problem, except that you do not have an objective function. So in optimization, you would have seen yesterday that you have an objective function which you are trying to minimize or maximize, and then there are decision variables, right? So and there would be constraints, right? So probably yesterday you might not have discussed constraints. So today we'll look into constraints also, how to handle constraints. So in these feasibility problems, we only have constraints. We don't necessarily have an objective function. It is just a set of constraints. We want to find out a solution which satisfies the set of constraints. So for example, timetabling can also be considered as a feasibility problem instead of an optimization problem. So there we want to schedule a set of lectures in a given set of slots. We are not necessarily trying to minimize or maximize. If we have an objective, well and good, but even without that, there are constraints for which a solution has to be found. So this map coloring problem has 6 countries: Netherlands, Germany, Luxembourg, Belgium, France, and Denmark. So what we want to do is that we want to use these 4 colors: blue, white, yellow, green, and we want to color these countries such that no 2 neighboring countries have the same color. So this is an example of a feasibility problem. Another example for feasibility problem is the Sudoku problem, which many of you might know. So here I have this row. I want this row and this column. Every row and every column I want to fill with the numbers 1 to 9, right? And each row should have unique elements. Each column should have unique elements, and each this 9x9 box which is highlighted should also have unique elements, right? So this is also an feasibility problem. So these are different solutions for this particular problem. So here, if you see, I have three solutions, right? So these are the constraints. Like we are not going to look into modeling these constraints, but this problem, when I say I can solve it as an optimization problem, I need to formulate whatever my requirements are there in terms of constraints. So this is an example for that model. So if I want to solve a Sudoku problem, this is the model that I am supposed to solve. Okay. So coming to optimization. So optimization has basically 3 major components. What we are looking at is basic optimization, right? So once we go into more detail, you will see that there are additional variables which bring in uncertainty and all those things. So that I am not covering as part of this introduction to optimization. So here we have decision variables. So decision variables are the variables for which I do not know the values, but I know the range. So for example, I have X, and X I know that I can maintain X anywhere between 0 to 10.
Hello,
right?
sir.
So this is my, yeah. Hello?
Whether sir's voice is audible to others?
Yes, ma'am. It is audible to us.
So audible.
Yes, ma'am. Okay. So I may have more than one variable. Let's say x is between 0 to 10, y is between 5 to 15, and z is between 8 to 12. So these are my bounds. So 0, 5, 8 is called as lower bound, 10, 15, and 12 is called as upper bounds. So once I have a decision variables, I also need to know in what range am I allowed to change that. And if you do not have a decision variable in a problem, then you do not have anything to optimize. So you need to give me that degree of freedom to vary. So here I am being told that vary x, y, and z in this domain such that some function, which is a function of x comma y comma z, is either a minima or a maxima. Right. So if there is an optimization problem, first thing is I need to identify what would be the decision variables. Once I know what are the decision variables, then I need to know what are the lower bounds and what are the upper bounds. So that is decision variable. And objective function is nothing but a relation of decision variable. So for example, if I say x square plus root yz, this is my f, and if I want to minimize, so this is my objective function. So this is what we are trying to improve, right? Either we want to minimize something or we want to maximize something. It is a relation of various decision variables. And then we have constraints. So these constraints provide restrictions on the decision variable. So for example, I have this constraint, x plus y should be less than equal to 10. So now I am allowed to change x and y within this domain, 0 to 10 and 5 and 15. But this relation should be satisfied, that x plus y should be less than or equal to 10. Right? So based on this decision variable, subjective function, and constraints, we can classify optimization problems, both problems as well as techniques. So for example, if you want to book a flight to from, let's say, Guwahati to Warangal, then my decision variables are this one, whether I go by Vistara, Air India, Air Asia, or whichever flight is. So these are my decision variables, right? So I need to have options. So if you tell me that there is only one flight, then there is nothing for me to optimize. So now here I can optimize either cost, like I can say I want to travel by the minimum cost flight, or I can also say I want to travel by the flight which requires the least amount of time, right? So I have two objectives. So we'll, if time permits, we'll look into that also, that how do I solve if I have two objectives. So any doubt so far? I would prefer, some kind of interaction. Without that, it is kind of boring.
No, sir. It's really quite okay.
Okay, thank you. So decision variables can be continuous, semi-continuous, or it can be discrete or sets. So for example, here a continuous decision variable is shown, x, which varies from 0 to 25, right? So there is any value which is 0 or greater than 0 and less than or equal to 25, the variable x exists, right? So x is a continuous variable. So in this case, I have a semi-continuous variable that, let's say that x is value of x between 0 to 10 is possible, and between 15 and 20 is possible, right? Any value which is greater than 10 and less than 15 is not permissible. So my bounds can be like this. So in this case, what we have something called a semi-continuous variable. The variable is continuous in the domain 0 to 10, and the variable is continuous in the domain 15 to 20, right? So these are semi-continuous variables. And then I have integer variables. Integer variables. So for example, if I say x belongs to 1, 2, 3, all the way up to, let's say, 10. So in this case, x can take only integer values, right? So it can take 1, 2, 3, or all the way up to 10, but it cannot take 1.1, 1.2. So that is not permissible. So usually when we are trying to model problems which require some kind of selection, we usually end up with this integer variables. So there are other type of variables which are commonly encountered. One is binary variable. So binary variable are usually represented by y. So y belongs to 0, 1. So if I know how to handle this integer variables, I can also handle this binary variables. So I consider this binary variables as a subset of this integer variable. And sometimes you can have sets. So for example, if you talk about this map coloring problem, so here I had to decide which country is to be painted by which color, right? So here if you see, I don't have, my bounds are not like 0 to 10 or anything like that. So here I have blue, white, yellow, green, or here if you see, I have these flights, right? So my decision variable is nothing but a set from which I need to select. So here, red, blue, green, yellow. So the decision variables can be a set. So if it is a set, you can very often model it as integers. So this is about decision variables. For most real life problem, the decision variables are to be bounded, right? It will not be between minus infinity to plus infinity, but theoretically, yes, a variable can be unbounded. So you can say the decision variable x has a lower bound of minus infinity and a upper bound of plus infinity. Okay. So any questions on decision variables? Okay. So objective function. So if I have an optimization problem, I need to have an objective function. So this is the function which we are trying to minimize or maximize, right? So it is a relation of the decision variables. So for example, if I have a two variable problem, f is equal to x1 square plus x2 square, then this is x1, this is x2. So this two-dimensional space. So there are points in this two-dimensional space. Every point in this two-dimensional space maps onto a point on the objective function scale, right? So when I have a single objective optimization, I only have this f, right? So if I say x1 is 2, x2 is 3, this transforms to a scalar value. So this point 2, 3 transforms to a scalar value over here. So that is f. So this is true in case of single objective optimization. So just like your variables are continuous, your objective function can also become semi-continuous. So for example, here if you see this variable x, this function f of x is defined from here to here, and then it is defined from here to here, right? So in between there is no definition for that function, right? That's because this variable is probably discontinuous. So because of that, your objective function is also discontinuous or semi-continuous. So most of the algorithms which we'll be studying would either be for minimization or it would be a maximization. So if I have an algorithm which solves a minimization problem, right, and if I come across a maximization problem, then instead of solving that maximization problem, I can actually solve minimization of minus f of x. So if you ask me to solve, let's say, maximize x square plus y square, let's say x plus y is less than equal to 10, and let's say there is some bound, x is equal to 5 to 10 and y is 12 to 15. So if I have this problem, and if I do not have an algorithm to solve a maximization problem, if I have an algorithm to solve a minimization problem, so what I would do is I will solve minimize minus x square plus y square minus of the entire function. I will not make any changes to my constraint. X plus y is less than equal to 10, x is between 5 and 10, and y is between 12 and 15. So if I solve this particular problem with a minimization algorithm, the solution that I get over here, right, will be the same as the solution for this problem. So if I solve this problem, let's say I end up with this solution, x is equal to 10 and y is equal to 15. If I end up with this solution, if I solve this problem also, the solution is same. X is equal to 10, y is equal to 15. Right? Only difference would be here, let us say this value comes out to be, let's say z, right? So the solution for this problem would be minus z. Only the objective function will have a change in sign for the solution also. So very often we end up doing x is equal to minus 10, y is equal to minus 15. So that is not correct. The solution occurs at the same point. X is equal to 10 and y is equal to 15. Just the objective function will have a different, will have the opposite sign. So that's why if you see most of the algorithms which you would be studying is with respect to minimization problem, but that can be used to solve maximization problem also. And if you do not have any objective function like Sudoku problem, you have the problem becomes feasibility problem, that you only have a set of constraints. So here this figure shows that minimization and maximization concept. So a simple one variable function if I take, so this is x and this is f of x. So if my function is this one, the one that is depicted over here, so for that function the minima occurs over here, right? If I take a mirror image of that function, it is like this, and if I take the maxima of this function, it occurs over here. So as you can see, the minima and maxima occurs at the same point, x star. So the solution remains same. This value might be different. This will be, let's say, 3, and this will be -3, right? So at the end of it, I solve it. I take x star as it is. Objective function value alone, I'll have to change the sign. I'll have to take the opposite sign. So any doubts so far?
So solution will differ, no, in case of maximization and minimization, if we are converting the maximization problem into minimization.
No, solution will not change because I am not, just 1 second, please. Here, if you see, so for example, take this function, right? So this function, the minima is here, right? If I take the mirror image of that, this function, where is the maxima of this function? It will occur at the same point. So x star will be the same. The solution would be the same. Solution, when I say solution, I mean decision variables. So if I have a problem like this, let's say maximize x square plus y square, and let's say x plus y is less than 10, and let's say xy should be less than equal to 25, and let's say I have bounds on x and y. So instead of this problem, if I solve this problem, x square plus y square minus, and the same set of constraint, then I will get the same solution. The solution for this problem and the solution for this problem will be the same.
Okay,
Right?
thank you, sir. Got your point.
Yeah, because I'm solving negative of this.
Okay, thank you, sir.
Constraints, I have two types of, broadly there are two types of constraints. One is inequality constraints, the other one is equality constraints. So inequality constraints are represented like this. Let's say x1 plus x2 is less than equal to 10. And if I want to reverse this inequality sign, instead of less than, if I want to convert greater than or equal to, I'll have to multiply by -1 on both sides. So if you multiply by a negative sign, the sign would change, right? So constraints are in general denoted as g of x less than equal to 0. So even if I have a constraint which says x1, x2 should be greater than or equal to 5, I can convert it into a less than equal to form by -x1, x2 is less than equal to -5, right? So just like what we did for maximization to minimization, all constraints which are of the type greater than or equal to can be converted into less than or equal to. Then I have inequality constraints. So here when I have such constraints, what I mean is x1 plus x2, whatever values I get for x1 plus x2 should definitely be less than equal to 10, right? I am not forcing it to be 10, but it has to be less than or equal to 10. If I have an equality constraint, x1 plus x2 equal to 3, that means I want exactly 3, right? 3.00001 is also not allowed, and 2.9999 is also not allowed. Right, so here I am saying x1 plus x2 should be exactly equal to 3. So this is another type of, this is a linear constraint, this is a non-linear constraint. X to the power e minus x square minus y square equal to 5. So this is non-linear, and this is an equality constraint. So this is an example for equality constraint. Equality constraints typically arises when you have balances, like when you have a process and you want to do balances on those process, you end up with inequality constraint. So for example, when you go to market to buy something, you take, let's say, 100 rupees. So very rarely you go to the market to say that I will spend 100 rupees. Usually you go to the market saying that I will spend less than or equal to 100 rupees. Right? So very often constraints are of this type, but there are also constraints of this type. So let's say I have a block over here. Let's say this stream is coming in, this stream is coming in, and this stream is going out. So let's say this is X1, this is X2, and let's say this is X3. So if no accumulation is to be done inside, then X3 has to be equal to X1 plus X2. So this is an equality constraint, right? This has to be satisfied. If this is not satisfied, then this tank will start accumulation. Any doubt so far? What is the difference between what is an inequality constraint, what is an equality constraint, and how to convert less than equal to or greater than equal to? Okay. So any solution, so when I say solution, it is value of decision variable. So if you give me a 10 variable problem, you give me lower and upper bound for those 10 variables. And if I am able to select a value for each of the variable, that is what I am calling it as a solution. Very often solution we use to denote the final solution which we get at the end of a process. So that's not what is meant by solution. Any solution for a solution is one for which I have values for all the decision variable. So if you tell me X is between 10 and 15 and Y is between 20 and 30. So if I tell X is equal to, let's say 12 and Y is equal to, let's say 18, this is a solution, right? I am not saying that this is the best solution or this is a worst solution. It is a solution, right? So a solution can be classified as feasible solution or infeasible solution. So a feasible solution is a solution which satisfies all the constraints. So if I have 1000 constraints, and if I have a feasible solution, it has to satisfy all the constraints, right? It cannot violate even one constraint. Infeasible solution is one which violates at least one constraint. So if a solution violates even one constraint, it is called as an infeasible solution. So one easy way to remember is let's say the requirement for someone to go from standard first to standard second, let's say they need to score 40 in all subjects, right? So if there is a candidate who scores 40 in all subjects, that candidate will move from first standard to second standard. But consider a candidate who has scored 100 out of 100 in 4 subjects and in the 5th subject scores only 39, right? The candidate would not be passed because the candidate has failed in one subject. So there the constraint was in each subject you need to score 40, right? So if you score in each subject, if you score 40, then you are satisfying the constraint requirement and hence the solution is feasible. Any doubt in that? What is a feasible solution and what is an infeasible solution? Okay. So this is an example for feasibility of a solution. Let's say I have a function like this, minimize f of x, and c is a constant whose value is given. Let's say in this case 0.065, and the objective is to minimize this. So pi x1 square by 2 plus pi x1 x2. So the question is, for what value of x1 and x2 will this function be minimum, right? But the value of x1 and x2 should satisfy this requirement that pi into x1 square x2 by 4 should be greater than or equal to 300, right? So this is the constraint that any value of x1 and x2 which when plugged on this left hand side, if it is having a value of greater than or equal to 300, then it is a feasible solution, else it is an infeasible solution, right? So now let us consider these two solutions, x1 equal to 3, x2 is equal to 10, and over here x1 is equal to 8 and x2 equal to 6, right? So in this case, if I calculate the objective function, if you plug in this 3, 10 in this objective function, you will get 7.05. And if you calculate this right hand side, pi x1 square x2 by 4, if you calculate, you will see that you will end up with 70.69. So this is an infeasible solution because it does not satisfy this constraint. On the other hand, this solution 8, 6, it has an objective function value of 16.34. And when I compute this left hand side of this constraint, I get 301.59, right, which is greater than 300. Right. So in this case, solution 2 is a feasible solution, right? And if I'm asked to select one of the solution, I will not blindly go by the objective function. So objective function is minimize f. So minimize f means 7.05 is better than 16.34, right? But I will not choose 7.05 because it violates the constraints, right? So you would always prefer a solution which is feasible, no matter how bad its objective function is, in comparison to a solution which is infeasible, right? No matter how good its objective function is. Is this clear? Any doubts? Okay. So we'll just take a small problem and just keep adding features to it. So right now this is a unconstrained optimization. How many variables are there? There are two variables, x1 and x2, two variables. There are no constraints. So this is an unconstrained optimization, right? And if you solve this problem, obviously you know the solution for this is x1 equal to minus infinity, x2 is equal to minus infinity, and f is also equal to minus infinity. So let me add bounds to it, right? So now what my problem is, minimize f is equal to 3x1 plus 2x2 subject to the condition that x1 has to be between 100 and 700 and x2 has to be between 50 and 100, right? So previously my search space was infinite. So now if you see, I have x1 100 700, so only any value between this is accepted with respect to x1, right, including the feasible region, but x2 has to be between 50 and 100, right? So since x2 has to be 50, this region cannot be feasible and this region cannot be feasible, right? So now my total feasible region is this one, right? So my solution lies in this feasible region. So in this case, the solution would lie at this point, x1 equal to 100, x2 equal to 50, for which if you calculate the objective function, it will be 400. So this is the feasible region just because I have my bounds, right? Now let us add one more constraint to it. So let me say that I have this equation, x1 minus 3x2 should be greater than or equal to 400, right? So I want to minimize f is equal to 3x1 plus 2x2 subject to the constraint that x1 minus 3x2 should be greater than or equal to 400, and the domains of x1 and x2 are 100 and 700, and here it is 50 and 100, right? So now what if I want to visualize the feasible region, what I would do is I will draw this line, right? So to draw this line, what you can do is you can consider this constraint as equality, because I want to draw this line, right? Once I draw this line, I will identify which region is greater than 400. So I'll put x1 is equal to 100, find out the value of x2. I'll put x2 is equal to 0, find out value of x1. So now I have 2 points, 0 comma minus 133.33 and 400 comma 0. So I can draw this line, right? So once I draw this line, I'll have to identify which region is feasible. So I let's say you can take any point. So for example, if I take this point 50 comma 100, and if I substitute in this 50 minus 300 is greater than 400. So if I substitute this point, this is what is happening in this constraint, right? So this relation is not valid, right? So this point, wherever this point is, that side is completely infeasible. So this region is infeasible. So now my feasible region is only this shaded triangle, right? So if you have more and more constraints, you will have your region being truncated, right? And sometimes, very rarely, you can even have an object constraint on the objective function itself. So for example, here we have shown that there is another requirement which says f should be greater than or equal to 1800, right? So when I say this f greater than or equal to 1800, then I can draw this. Just 1 second. Okay, so f is this one, 3x1 plus 2x2, right? So what I'm saying is f greater than or equal to 1800, is nothing but 3x1 plus 2x2 should be greater than or equal to 1800. Similarly, I can draw this line, right? And I can identify which region is the feasible region. So in this case, this triangle, the shaded area is the feasible region. So this is just to show like more and more constraints you have, your feasible region starts to shrink. So it might seem like now you have a very little space to search, right? But now you are pictorially visualizing it. For a large problem which has hundreds of variables and hundreds of constraints, it is not possible to identify what is the feasible region graphically, right? So whatever algorithm you are using, it has to do all this work. It has to understand where is the feasible region and then search in the feasible region. I hope at least on this slide we'll have few doubts. Any doubts in this? Okay.
No, sir.
So this is a problem with a larger number of constraints. So here I have minimized 3x1 plus 2x2 such that these constraints 2x1 plus x2 is greater than or equal to 5, x1 plus x2 is less than or equal to 4, x1 minus x2 is less than or equal to 2. So what I can do is I can plot all these three lines, right? And for each of the line, I can identify what is the feasible region, right? So in this case, it happens that this shaded area is the feasible region. So the optimal solution has to be searched from this feasible region. This problem is an infeasible problem. So this is a feasible problem. Feasible problem is in like the problem has a solution, right? So now it is up to the algorithm. Is it good enough to find the solution? This problem to begin with, it is an infeasible problem, right? So here, if you see, you will have conflicting constraints. So all these three constraints, if I plot, so this is 4x1 plus x2 equal to 5 is this line. So this constraint says that everything below this is feasible, right? This constraint says everything above this is feasible, and this constraint says everything below this is feasible. So now if you see, there is no common area in which all the three constraints are feasible, right? So then the problem itself does not have a solution. So now your algorithm, no matter how good it is, it cannot find a solution because the problem inherently is infeasible problem. So in optimization context, we very often use what is called as contour plot. So contour plot is the curve which has identical objective function value, right? So for example, if I have this function x1 square plus x2 square, so I'm fixing the value of f as 20, right? And I'm taking some value of x1, finding out what is the value of x2, at which I will have f of x is equal to 20, right? So and then if I plot these points 2, 4, 4, 2, and all these points, I will get this curve. So this is the contour with an objective function value of 20, right? So similarly, this is the actual contour plot. So I can plot, so what I showed you was this curve. Similarly, I can plot for 10, 5, 3, 2, and so on. So this shows like what is the value of the objective function in the search space. So throughout this ellipse, the value of my objective function is 20. Then we have something called as realizations. So realizations are solutions which have the same objective function value but different decision variable values. So for example, consider this problem in which we are asked to design a can with certain diameter, right, and certain height, such that the can should have a volume of at least 300 ml, right, and the cost of painting it should be minimum, right? So that problem can be modeled like this, right? So this is the volume pi d square h by 4, so that has to be greater than 300, and the cost of painting, let's say per unit, is 0.065. So the amount of painting that I need to do, the area is pi d square by 2 plus pi d h into c, right? And here d and h can take any value between 0 to 31. That is the constraint which is given. So in this case, as you can see here, I can have two cans, this can or this can. Both of those cans have the same objective function value, 22.87. but this one has a diameter of 8 and a height of 10. This one has a diameter of 5 and a height of 19.9. So both of these solutions are called as realizations. It is the same objective function value that can be realized by two different sets of decision variable. So 8, 10 as well as 5, 19.9 give you the same solution of f is equal to 22.87. So when you do, since you have already done genetic algorithm yesterday, you will see that at the end you will end up with a population, right? You will get the best solution, but on top of the best solution, you also have something called as the population, right? So the population will now have 100 solutions. So those 100 solutions, or whatever is your population size, that may have realizations. Many of the solutions might have the same objective function, but could have different decision variables. So those are called as realizations. So let me kind of go to this, right? So when we say we have an optimal solution, what we want is the globally optimal solution, right? So for example, if this is the function, right? This solution is a local optima, this solution is a local optima, this solution is a local optima, because all of them are minima, right? So the gradient at those points vanishes, right? But what I am interested is this point, the global minima. What is the lowest possible value if I'm going to solve for a minimization problem? So what is the least possible value? And if I'm solving a maximization problem, what is the maximum possible value for any function? And I do not want to get stuck in these points, right? My aim is to reach the global optimum. So very often when algorithms are being discussed, you will come across this term, local optima, global optima, and all those things. Fine. So now we'll go to classification of the problems. So maybe particularly for that hands-on session, this slide is very important, because depending upon given a problem, you will have to first classify what is the type of problem, and based on the type of problem you will be able to select a solver, right? So not all solvers are capable of solving all this problem. So it's important for you to understand how to classify the problem. Based on the classification, you will select techniques, right? So even if you are thinking that I'm not going to solve a problem by pen and paper, you are going to use software. So even in software, you have this requirement that you need to select appropriate function, and those functions are based on the type of problem, right? So here we are discussing primarily 4 types of problem. One is linear programming, another one is non-linear programming, another one is mixed integer linear programming, another one is mixed integer non-linear programming. Okay. So we discussed that optimization problem consists of decision variables, objective function, and constraints. So this classification is based on using this, right? And variables, we have said, like we discussed that the variables are either continuous or discrete. For this classification, we are not considering semi-continuous variable, but there are variables which can be semi-continuous. But for this classification, we are only considering 2 types. Either it is continuous or it is discrete. The objective function can either be linear or non-linear. It's a function, right? So you can classify it as linear, non-linear. Constraints also, I can classify it as linear and non-linear. So for a linear programming problem, right, my variables are continuous, right? I am not allowed to have discrete variables, right? And my objective function as well as my constraints are linear, right? So the functions are linear, the variables are continuous, right? So when you have that scenario, you have something called as linear programming, right? For non-linear programming, I have variables which are all continuous. I am not allowed to have integer variables or discrete variables. My objective function can either be linear or non-linear, and my constraints can either be linear or non-linear, but I have at least one non-linearity, right? It can either come in objective function or it can come in constraints. I can have more than one non-linearity, but I need to have at least one non-linearity to classify it as a non-linear programming. So any doubt in that? What is a linear programming problem? What is a non-linear programming problem? Okay. So then I have this mixed integer linear programming problem. As the name indicates, it's mixed integer, right? So it means I have continuous variables as well as I have discrete variables, right? And here it is linear. So my objective function is required to be linear, and my constraints are required to be linear. Non-linearity is neither allowed in constraints nor allowed in objective function. Mixed integer linear programming problems. Then I have mixed integer non-linear programming problems. So here my variables can either be, some of my variables are continuous and some of my variables are discrete. My objective function is either linear or non-linear, right? Both are allowed. And my constraints are either linear or non-linear, right? But at least one constraint or the objective function is non-linear. So I have these 4 types of problems: linear programming, non-linear programming, mixed integer linear programming, and mixed integer non-linear programming. And then I have integer linear programming can very often be considered a subcase of mixed integer linear programming, wherein I don't have continuous variable, right? My objective function is linear, my constraints are linear because I have linear over here, right? And my variables are discrete. All my variables are discrete. I do not have continuous variable. Any doubt in this? Okay, so genetic algorithm can solve which type of problem? Can it solve linear programming problem? That's what I said, right? We want to classify this so that you know which technique can solve which type of problem. So now the question is, genetic algorithm. This is just a problem, right? Here you may think that I did not teach linear programming. Right now what we are saying is what is a linear programming. We are not talking about how to solve a linear programming problem. So now the question is, if I have a linear programming, let us say this is an example for linear programming problem. Okay. So this is an example for a linear programming problem. I want to minimize z is equal to 4x1 minus x2. These are my 3 constraints, right? Now you know genetic algorithm. So can genetic algorithm be used to solve linear programming problem? Yes, no, some comment? Or
So genetic algorithm must be non-linear.
okay. What will happen if I use genetic algorithm to solve a linear programming problem? Will it not solve? It can solve non-linear. Very good. Agreed. Right? The question is, can genetic algorithm solve a linear programming problem? So genetic algorithm is just an example, right? So if you have done particle swarm optimization, TLBO, or whatever you have done, can it solve such problems, such linear programming problems? Okay, let me simplify it. What if I don't have these constraints? Let's say I have only this: minimize z is equal to 4x1 minus x2. So can you use genetic algorithm to solve it? So if you are not knowing the reason, then at least tell me, think, where will you get stuck? What does genetic algorithm initially do? What is the first step in genetic algorithm? So I want you to think about that and see, like, because of this reason I cannot solve this particular problem. using genetic algorithm? Where will you get stuck? Or is there no way no place that you will get stuck? It will work perfectly fine.
We may get stuck in the encoding step, I think.
Sorry?
We may get stuck in the encoding step, I think.
Encoding. So I have two decisions. So what did you do? Did you do a real coded genetic algorithm or binary genetic algorithm?
So we discussed 2 to 3 some forms of encoding like postfix, prefix, hexa, octal, binary, and all.
Okay, fine. Good. So whenever you are learning a technique, have this problem in mind and see if this problem can be solved with that technique. Right? Otherwise, like what will happen is you will know a range of technique, but you will not know how to solve a given problem. Okay. So let me go back to what we were doing. Okay. Good. So genetic algorithm technically can solve all of these types of problem. Not only genetic algorithm, pretty much most of the techniques which you are going to see as part of this course, PSO, TLBO, they can be used to solve all of this. Right? But there are special solvers for, let's say, LP, MILP, which probably in the second lecture we will show you. So okay. So this is a general representation of any optimization problem. So minimize z is equal to f of x comma y. So I have a objective function which has variables x and y, and I have constraints g of x comma y is less than equal to 0 and h of x comma y equal to 0. So here y is indicated to denote a set of binary variables, right, or integer variables, and x is denoted to represent a set of continuous variables. Right? So it's just not one variable. Let's say I have n such variables. Okay, and I have the lower and upper bounds for x and y. Right. So here y is an m-dimensional integer variable. X is I have n such variables. So I have x1, x2, x3, all the way up to xn, and I have y1, y2, y3 all the way up to xn. So the number of continuous variable and the number of integer variables need not be same. So I can have a problem in which there are 100 continuous variable and only 5 integer variables. So optimization techniques we can broadly classify into 3 types. One is mathematical programming techniques, the other is meta-heuristic techniques, and the third one is other techniques. Right? So this is a classification more based on how I perceive it. If you look at different books, they might be classifying it in a different way. So mathematical programming techniques, you have these techniques are built on the basis of geometrical properties of the problem. So for example, if you go to this linear programming problem, let me just get rid of this. Right. So here if you see, I have this problem, minimize z is equal to 4x1 minus x2. I have this constraint 2x1 plus x2 is less than equal to 8. So if I draw that line, this is that line, 2x1 plus x2 equal to 8. Since it is less than equal to 8, the feasible region is everything below this line. Right? It is not shaded because of the other constraints. This area goes out. So that's why it is not shaded. Because as far as this constraint is concerned, everything below this line is feasible. Right? So, and then I have this constraint x2 has to be less than equal to 5. So this is that constraint x2 is equal to 5. So everything below this is feasible. Right? And then I have this constraint x1 minus x2 is less than equal to 4. And I also have this constraint that x1 has to be greater than 0. So x1 has to be greater than 0. I have this line and everything else is kind of on the left hand side is gone. And I have this constraint x1 minus x2 equal to 4. So now if you see, this is for this particular problem, there is a there is a mathematical proof that the best possible solution would lie on the vertex. So it is either here or here, or it is here or it is here, right? So if I have a linear programming problem, there is a guarantee that the optima in the sense we are looking at globally optimal solution. So the globally optimal solution lies at one of these points. So that is a theoretical property is there. So if I have a linear programming problem, I will not use GA. What the question that previously I asked is, can I use GA? The answer to that is yes, I can use GA to solve a linear programming problem. What I am saying is GA may not be the best algorithm to solve it, because if you have a linear programming problem, then you have methods such as simplex method and interior point methods, right, which can be used to solve this problem. And once simplex method completes, right, whatever solution you are getting is guaranteed to be globally optimal solution. But if you use genetic algorithm or TLBO, even after it completes, whatever solution you get, there is no guarantee that it is the best possible solution, right? So that's why it is important to classify the problem, and then you see whether based on that classification, whether it is linear programming or not. If it is linear programming, you can use simplex method to solve it. Any doubt so far? Okay. And then I have, go back over here. Right. So if you have linear programming, you have something called a simplex method, which you can use to solve. If you have mixed integer linear programming, you have something called as branch and bound. Right. Branch and bound, what it does is it solves a series of simplex problems. Right. You may have one problem, but it will solve a series of simplex problems. And finally, whatever solution you get using branch and bound will be globally optimal. Right. So even in this case, genetic algorithm may not necessarily be a good option. Not only genetic algorithm, most of these meta-heuristic techniques may not be necessarily a good option for LP and MILP. Right. So in those cases, it might be a better idea to go with these techniques, right? Particularly simplex method and branch and bound for linear programming and mixed integer linear programming. Okay. So if you have nonlinear programming or mixed integer nonlinear programming, right, neither there is a guarantee among these techniques, nor there is a guarantee among these techniques that you can find the globally optimal solution. So what I am talking is an arbitrary nonlinear programming problem. So for an arbitrary nonlinear programming problem or a mixed integer nonlinear programming problem, NLP or MINLP, you don't have a technique which can guarantee you global optimal solution. There may be techniques which can find it out, but then at the end of it, there is no guarantee that this is the algorithm has found the best possible solution. Okay. So that is with respect to single objective optimization, right? In multi-objective optimization, what I have is, so this is a classical example from this book, Professor Kalyan Mahdev's book. So here I have, let's say, two objectives. One is cost, another one is comfort. I want to go and buy a car which has the least cost, right? So cost I want to have low, and I want to have high comfort. Now in market, as you know, you may have a car which is very cheap but does not have a high comfort. So let's say the cost is 1K and the comfort is just 30%. I also have cars whose cost is very high, 100K, and comfort is also very high. So let's say I have 90% comfort over here. So between car 1 and car 2, if I call this as car 1 and this as car 2, which one is better? Would we be able to tell which one is better? If I ask you the question between car 1 and car 2, which one is better with respect to cost? If I ask that question, then you will say one is better. If I ask you the question, which one is better between 1 and 2, with respect to comfort, you will say 2 is better. My question is, cost and comfort both are equally important to me, right? I cannot say cost is more important or comfort is more important. That is the problem. That is the problem that you are intending to solve, that I want to find out solutions which have the least cost as well as the maximum comfort. In that case, is it possible to say which one is better, 1 or 2? There was someone was saying something, but probably I did not let the person speak. I just wanted to finish that statement. So between 1 and 2, which one is better? Okay. So between 1 and 2, it is not possible to say which is better. So when you have multi-objective optimization, you don't necessarily get one solution. You will have a series of solutions which are called as a set of non-dominated solution or Pareto friends, right? So set of non-dominated points or the Pareto points, right? So in multi-objective optimization, this is what you are intending to find, right? Another example is that same flight. Now I am saying my objective is not just to find out the least cost. I'm interested in least cost as well as least time. So there may not be flights which satisfy both of them. Some flights might be cheaper, but their travel time might be higher. Some flight might have lower travel time, but their cost may be higher. So I have two objectives which are conflicting one another. So in multi-objective optimization, when you say a multi-objective optimization, in the context of optimization, it is not just there is one more than one objective. It is there is one or more objectives which are conflicting with each other. That if I try to improve one, the other one gets deteriorated, and if I try to improve the other one, this one gets deteriorated. So that is multi-objective optimization, and I do not get a single solution. I will get a set of solutions. So all these points, if you consider them to be as cars, right? This is 1. Let us say this is 2. This is 3. This is 4, and this is 5. Right, all these cars are non-dominated solutions. So would you be able to pick a car between 4 and 5? Okay, so it's not possible to pick a car between 4 and 5. 4 is less in cost, right? But 5 is good in comfort, right? Similarly, you have 3. 3 is less than 4, has lower cost than 4, but also has lower comfort, right? Comfort I am trying to maximize, cost I am trying to minimize. So all these 5 form a set of non-dominated solutions or Pareto points. Right? So this is what we had discussed in single objective optimization. Let's say I have a problem which is x is equal to x1 square plus x2 square plus x3 square. So if you tell me x1 is 2, x2 is 4, and x3 is 7. So this 2, 4, 3 is a point in this 3-dimensional space, right? When you had single objective optimization, when you calculate objective function, each point over here comes into this uni space function, right? It comes to just one point. In multi-objective optimization, what happens is I have this objective function f1 and this objective function f2. So the same point 2, 4, 3 transforms into a 2-dimensional space. So every point in this 3D space has a corresponding point in the objective function space. So this is the objective function space, right? This is also objective function space. This is the decision variable space. So every point in the decision variable space previously had just one value. So it was 1D, right? Here, every point in the decision variable space comes into a 2D, right? 2D because I have 2 objectives. If you have 3 objectives, then this will transform into a 3D point, right? So previously you are searching only in this. Now you are searching in this as well as in this, right? Because you are trying to find out the set of non-dominated points. So this problem is relatively more difficult to solve when compared to this problem. But most of your problems are multi-objective problems. Very rarely you will have problems. I mean, in while learning, we give you just a single objective, you solve it using single objective, and that's how things get over. But real life, if you go out there, you will see that there are more than one objective which you want to satisfy at any given point of time. So let us say I have these 5 points, 9, 2, right? So I have a solution 1. So solution 1 has some decision variables. For those decision variables, if I calculate F1 and F2, let us say I get 9, 2, S2 I get 8, 5, S3 I get 12, 1, S4 I get 11, 3, and S5 I get 16, 2, right? So now the question is, among these 5, which are the non-dominated points? So would you be able to kind of, you want to try it out and tell me what are the non-dominated points? So which one is better? S1 is better or S2 is better between S1 and S2? I'm not going to do anything unless you people tell me the answer for that. I want to maximize F1 as well as I want to maximize F2, right? So is 9 better than 8?
But sir, in other case, 2 is not better than 5.
Very good. Right. So between S1 and S2, I cannot say which one is better. Between S1 and S3,
Here also we can't say anything because in first case it is going to be minimized, and in second case it is perfect, means to say 2 is greater than 1.
between S1 and S4,
Yeah, then S4 is the must be the solution for this.
so S4, as of now, what I can say is S4 dominates S1, right? Because I have to do all the comparison.
Yes, sir.
Not only S1, S2, S1, S3, I also need to make S2, S3, S2, S4, all those comparison I need to make. Right now, what I can say is I will never select S1 as long as S4 is there. Is that correct?
Yes, sir.
Right. So right now I have kind of got rid of S1. Now the question is S2. Is S2 better than S3?
No.
S2 better than S4?
No.
S2 better than S5?
No.
Right. So I cannot throw out S2. Correct. So like that, I have to make the comparison with S3, S4, S5 and S4, S5. Then you will be able to see that S2, S4, S5 forms a set of non-dominated points. So for example, S3 I can get rid of, right? Because as long as I have S5, 16, 2, so 16, 2 is better than 12, 1. We saw that S1 can be, we can get rid of S1. So I can also get rid of S3 because this point completely dominates S3, right? So these 3 points constitute my Pareto front. So if you like, just 1 second, let me see what you have done so far. Okay. Fine. So for example, ant colony optimization, when you had done, you were seeing only in the context of decision variables, right? So if you had decision variable x1, x2, x3, and if your objective function was, let's say, x1 square plus x2 square plus x3 square, your ant colony optimization will give values for x1, x2, x3, and then you will calculate f and return that. That's what was happening in those optimization algorithms when you are solving single objective optimization. When I am solving multi-objective optimization, in addition to whatever you are doing in single objective optimization, I also need to find out which are the best solutions. Right? Previously, it was easy. Let's say in single objective optimization, if you give me 5 solutions, let's say 4 solutions, 2, 8, 9, 7, right? If you ask me what is the best solution with respect to maximization, I can easily say S3. Because I had a vector, I need to just find out what is the maximum element in that vector. When I have a multi-objective optimization, I will end up with a set of non-dominated points. So between 2, 4, and 5, I cannot tell which is better. So these points, what I'm calling is non-dominated, right? There are no other points which dominate these points. So S2, S4, S5 are non-dominated points. There are no other points in the search space which dominate this. So in multi-objective optimization, this is my aim. I want to find out the Pareto solutions. Any doubt in that? What are Pareto solutions? So Pareto solutions very often can better be understood if you are a cricket fanatic. Then probably you want to have a team, right? In the team, you don't always select the best batsman in India, right? You select few batsmen who are best in India, then few bowlers, right? So there you have kind of 2 or 3 objectives, that someone you needs to do fielding also better, someone needs to be good at bowling, someone needs to be good at batting. So it's like you are trying to find out a team. Now no one is better. That is what is the assumption, that no one is better than those people. Those people have their qualities. So for example, the opener batsman may not even be able to bowl, and the guy who is bowling may not even be able to kind of stand for 1 over, right? But still they do have a place in their team, despite the fact that there is some other batsman in India who did not find a place, right? Because there you are looking at multiple objectives. You want batting skills as well as you want bowling skills. So multi-objective optimization occurs only if the objective functions are conflicting, right? Let's say I have 2 objective functions, max, max. So very often it is considered that if for conflicting objective functions, I need to have 1 min and 1 max. That is not correct, right? I can have 2 functions, max, max. Both the functions are to be maximized, but they are conflicting, right? So it depends upon the problem. What is your search space? What are your constraints? What is your objective function? Depending upon that, you will be able to tell whether they are conflicting or not. So for example, here if you see, if my domain of my decision variable x is between 0 to infinity, right? Then x square or x cube is not even conflicting. I can ignore this. I can just solve this. Whatever x I get, that is the optimal solution for this also. Or I can ignore this, I can just solve this, and whatever solution I get is also a solution for this, right? Because in this area, 0 to infinity, they are not conflicting. As x increases, y also increases, or f of x increases. But if I convert my domain to minus infinity to 0, right? So now if you see, as I increase x, my f1 is increasing, my f2 is actually decreasing, right? So here I cannot ignore either of this function. I need to take both the functions together and then try to optimize and get a set of Pareto points, right? So just looking at the function, and looking at this max max, you cannot say that they are either conflicting or non-conflicting. It depends upon the constraints as well as your decision variables. Based on that, you will be able to take a call whether they are conflicting or not. Okay. So for now, you can just focus on this, right? So if I have 2 objective functions, f1 and f2, right? I'm actually, so if this is my space, objective function space, then I'm actually looking at these solutions, not all the corner solutions, right? So for example, this solution is not a Pareto solution. Why this solution is not a Pareto solution? Because I have some other solution. So this solution has this one, whereas this solution dominates this solution because you have a better lower f2 and lower f1 when compared to this particular point, some particular point over here. So it is not all the edges, it is the edges which are kind of being non-dominated. So no other point dominates it. So this is the Pareto front for a minimization problem, wherein you are minimizing f1 as well as you are minimizing f2. So depending upon other problems, min max, max max, max min, you can identify what is the region. So in this case, the region is 0, 0. So you are trying to go over here, all the points which are pointed in this direction, 0, 0, 0. When you have min, max, you are looking at points which are pointing towards 0, infinity. F1 is 0 and F2 is infinity. Over here you have infinity, 0, and over here you have infinity, infinity. Okay. So just like you had realizations in single objective optimization, you can also have realization in multi-objective optimization. So two different points in the decision variable space. So my decision variables are x1, x2, x3. So two different points in my decision variable space can map to the same objective function value, right? So for example, these two are decision variables are different, but they are depending upon what is f1, what is f2. I can have same f1 as well as same f2. So value of f1 is 125 for both solutions, and value of f2 is 42 for both solutions, right? So this is realization in the context of multi-objective optimization. So any doubt so far? I mean, unless many of you are faculty, so when you go and teach, and if no one is asking anything, then there are two reasons. Either whatever we are saying, the students also already know it, or they have not necessarily got what we have said. There is no point in just me coming and telling whatever I know. The whole point is that I should be able to tell whatever I know in a form in which you are able to understand.
Sir, so actually in the car
Yeah.
example, I think you can like take a ratio of the cost to comfort, right, and try to tell which car would be better. And you can probably also do that for like other Pareto examples, like Pareto optimization examples.
Fine. So I will come to that. So probably if I have understood the question correctly, so let's say I have been given minimize F1, minimize F2. I have not been given any other information, right? Both the objective functions are to be minimized, and both of them are conflicting. I am asked to solve this problem. I am not given any other information, right? If I have been given some information saying that F1 is more important than F2. So for example, if you tell me cost is more important than comfort, then I will totally ignore comfort. I will tell you that car 1 is best. So here the whole point is that I have not been told that what is, what do you say? Any type of information, precedence information that F1 is better than F2 or F2 is better than F1, that is not told. So what you were saying is, instead of doing this, I can minimize F1 by F2, some ratio of it, or I can minimize W1 F1 plus W2 F2.
Oh, okay. So actually, so actually, what I was saying was, so you had asked which car was better. So then I thought we could answer that by taking which car offers the best comfort to cost ratio. Like that is what.
But that was not my question. So the question is, since it's a car example, we are able to come up with that logic. But given two functions, function F1 and function F2, I want to find the set of points which are non-dominated. Right? It might happen now if both of these objectives are not conflicting. For example, if you go to this particular problem, if I solve this problem, I'll get only one solution. Though it is a multi-objective optimization, I'll get only one solution, x is equal to infinity. There are no Pareto points, right? Because the objective functions are not conflicting. So if you are able to come up with something like this, that if you are able to say, what did I write? If you are able to say that solving this problem is the same as this problem in your context, then yes, then I have converted a multi-objective optimization problem into a single objective optimization problem, and then I can solve. So for example, here people might say that I will give 80% weightage to cost and 20% weightage to my profit. 80% weightage to my cost and 20% weightage to comfort. So if you are able to give that information, then it becomes a single objective optimization. The whole premise is no such information is available. I am being told that F1 and F2 are equally important.
Oh, okay. Okay, sir.
Okay. Any other question? Fine. Okay, so what I'm going to do is that predominantly in this course, you are actually studying meta-heuristic techniques, right? Meta-heuristic techniques, usually when they are developed for unconstrained optimization, right? That you have only objective function. So probably most of the lectures will focus on, let's say if I have a function like this, minimize f is equal to, let's say, sine x1 plus some, let's say, cos x2 or some complex function, how to minimize this or maximize this, that's what you would be seeing. So what I am trying to just motivate here is that there are constraints. So you can have problems like this. So for example, this particular problem. So forget this, don't look at this part. If you look at this part, then you will get confused, right? So what most of the lectures are going to do is how to solve this particular problem. So what is the value of x1, x2, x3 for which this function is minimum, right? So the objective function may not be this simple. Here it is linear, but they will be showing you on non-linear functions, right? So what I am trying to say is that such problems are very rare, right? Unconstrained problems are extremely rare in real life because every time you have constraints, right? Whatever you want to do, you do have constraints on that. So what we are trying to do is, what if happens, how do I handle if I have these type of constraints, right? So all those genetic algorithm, whatever algorithms you have seen, so most of them would be doing this. So you have an algorithm and you have a problem, right? So the algorithm may be sending decision variable values, right? Not once, but multiple times. So for this particular problem, it will send the value of x1, x2, x3, and your problem will be sending the value of objective function. So it will calculate what is 3x1 plus 2x2 plus x3. So that will be a scalar value that would be returned, right? So most of the algorithms are developed for unconstrained optimization, and this is how it works, right? So that is only if I have f, right? But now my problem is I have this objective function as well as I do have my constraints. So how do I take care of my constraints, right? Okay, so to understand, to do that, this is again just brushing up of whatever we have seen. So you can have inequality constraints, you can have equality constraints. So inequality constraints are denoted by g of x is less than equal to 0, and if it is of the other type, you can multiply by a minus sign and reverse. You can multiply by -1 and reverse the sign. And feasible solution, infeasible solution, right? So feasible solution is one which satisfies all the constraint, and infeasible solution is one which violates at least one constraint. So there may be 1000 constraints, it may satisfy 999 constraints, it is just violating one constraint. Even then it is an infeasible solution. Okay, so if you have, let us say, if I give you solution S1 and solution S2, if this is feasible, if S2 is also feasible, which one would you prefer? I have two solutions, right? Both of them are feasible. Which one would you prefer? So let us say I have 5 subjects, right? I have 2 candidates. Both the candidates have scored more than 40 in both the subjects, in all the 5 subjects. Candidate 1 has scored 300 total. Candidate 2 has scored 350. So now if I have to select based on marks, which one would I select?
So maximum marks means say S2 will be the solution.
S2, right? So because both of the solutions were feasible, both of them cleared all the 5 subjects, right? So if both are feasible, then I will go by objective function value, right? Now the question is, let's say I have student 1 who has a total of 439, and I have student 2 who has a total of, let's say, 200. So this 200 is scored by 40 into 5. All 5 subjects he has scored 40, 40, 40. This 439 is scored as 4 into 100 plus 39. Right? And the requirement is for a student to go from one standard to the other standard, the student has to score at least 40 in each of the subject. So who will go to the next standard?
Sir, S2.
S2, right? Why S2? S2, if you see the total of S2 is less. So even then, why are we preferring S2?
Because S1 is infeasible solution.
This is infeasible, right? So let's say the third case. So this is one case in which I had both the solutions as feasible. In this second case, I had one infeasible, one feasible, right? So if I have infeasible and feasible, I will select feasible. If I have two feasible, I'll select the feasible which has a better fitness function value. And let's say I have two students, S1 and S2. This total is 195 and this total is 190. Let's say 199. Both of them have failed. Or let us say this student has failed in one subject. This student has failed in two subjects. So if I have to select one, whom would I select? Okay. So I would select S1 because the violation is less. The requirement was that the student has to pass in all subjects, right? If I'm going to compare S1 with S3 who has not failed in any subject, then definitely I will select S3. But if I have to select between S1 and S2, right, then I would select S1 because S1 has failed in only one subject. So those three rules are coded over here. So any feasible solution is preferred to any infeasible solution, right? Among two feasible solutions, the one having a better objective function value is preferred. Among two infeasible solutions, the one having a smaller constraint violation is preferred. So if I have constraint, I will see which one is violating the constraint by a smaller magnitude. So if I have a constraint like this, x1 plus x2 is less than equal to 10, and I have a solution S1, which when I calculate x1 plus x2 gives me 8, and I have another solution S2, which when I calculate x1 plus, this let's say it gives me 18, and this gives me, let's say, 20. Right, so 18 is also violating, 20 is also violating, right? So in this case, I have both infeasible solutions, right? If I'm made to pick one solution, I will pick this one because here the violation is only 8. 10 and 18, the difference is only 8 when compared to 10 and 20 where the difference is 10, right? So these are the three rules that we need to keep in mind when we have a constrained optimization problem. Fine. So let us take this small example, right? Let's say I have four solutions, S1, S2, S3, S4. And let's say for S1, the decision variable X took a value of 0.7. For S2, it took 0.4. For S3, it took 0.65. For S4, it took 0.8. And my objective function is F is equal to X by 2. So since I know X, I can calculate F. Right, and I also have a constraint which says that x square should be greater than or equal to 0.45. So this is my constraint, and in this case I have a nonlinear constraint, right? So here if you do 0.35 square, it is greater than 0.45, so the violation is 0, right? Similarly S4, the violation is 0. If you do 0.4 the whole square, the violation is 0. It is greater than 0.45. For these two, if I calculate, there is a violation of 0.29 and a violation of 0.0275. So here, if I have to pick one solution among all the four, which one will I choose? So will I choose S2 because it has only objective function value of 0.2 and I have a minimization problem? Will I choose S2? You understand what is this violation? This violation is I do 0.2 the whole square, right? And I see how much it is away from 0.45. Is it greater than 0.2? 0.2 square, is it greater than 0.45? Okay, fine. So if I have to select, then I will select, in the first place, I will select S1, because S1 and S4, both of them are feasible. There is no violation. So I will select S1, then I will select S4. Then if I have to select even more solution, I will see which one has lower violation, 0.29 or 0.0275. So if I have to select 3 solution, then I will select S1, S4, S3. If I have to select all the 4, then I will select first S1, then S4, then S3, and at the last S2. Okay. So if you have a minimization problem, right? So then we will define something called as fitness function. So fitness function is objective function plus lambda. Lambda is a very high scalar value into penalty, right? Penalty is how much I am violating. Based on that, I am going to assign penalty. So instead of my algorithm giving back my objective function, so previously it was returning only the objective function. Now what we are saying is the algorithm will send decision variable, but my problem will return my fitness function. So fitness function is going to be calculated as, for a minimization problem, your objective function plus lambda times penalty, right? So this is the logic for this can be understood by, let's say, the date to pay the fee is, let's say, 10th of every month, and if you delay it by every day, you need to pay 100 rupees extra, right? So my objective function is the fee. What is the amount of fee? So now if I'm violating the deadline, so if I'm violating the deadline by 5 days, so I need to pay 500 fine. So that's what we are doing over here, that my fitness function is objective function plus lambda times penalty. Penalty is incurred because I'm not satisfying the constraint, right? So now consider 2 solutions, S1, S2. Let the objective function of S1 be 5, objective function of S2 be 7. Let me say that for this arbitrary problem, the solution S1 is feasible, solution S2 is infeasible, right? So between these two, my algorithm is supposed to select S1, right? Because it is a feasible solution, right? Since it's a feasible solution, there is no violation. Since this is an infeasible solution, let me say for that arbitrary problem, the violation was 2, right? So now if with a lambda of 20, I can calculate the fitness function, which turns out to be 47, right? So if you are wondering where did I get this 5, 7, 2, right? This 2 is definitely not because 7 minus 5 is 2. So this 2 has nothing to do with the difference of this, right? It is like I have an arbitrary problem. For that arbitrary problem, I have some decision variable values. When I substitute those decision variable values into the objective function, I get a value of 7, and one of the constraint is being violated by a magnitude of 2. So that is why I have 2. Is this table clear? This one?
Yes, sir.
One, yes, I heard there was someone else who was probably trying to say something. Okay. So now if the algorithm has to select between S1 and S2, remember, I know I am drawing this diagram again and again, but the reason is the algorithm gets only 5 and 47. It does not get the information whether the solution is feasible or not, right? So based on this 5 and 47, it has to make a decision which satisfies these 3 rules. This top 3 rules, it has to satisfy. It has to make this decision based on just this f value, right? So right now with a lambda of 20, this seems to be fine happening. But let me say I have one more solution, S3, whose objective function value is 2, right? And it is also not feasible. The violation is very less, 0.1. So without looking into this fitness function, which one do you want the algorithm to select? If I have to select one solution among S1, S2, S3, which one would I select? I will select S1 because it does not have any violation, right? So I want algorithm to select 5, but what will the algorithm select is 4 because the minimum value is 4. I return the fitness function only. Remember, I cannot return this. I cannot return this. Once the algorithm gives me a solution, I can only return the fitness function. So in this case, if I take a lambda value of 20, and if I calculate the fitness function, it will be 4. So the algorithm will look into 5 and 4, and it will choose 4, but 4 is an infeasible solution. Right? On the contrary, if I take a lambda value of 200, right, this 5 will remain 5. So if there is a feasible solution, then there is no penalty at all. So no matter what your lambda value is, your fitness function is the same as your objective function. So now here I get 5, here also I get 5, because a feasible solution does not have penalty, and if there is no penalty, then your fitness function is same as your objective function. For this solution, 7 becomes 407 and 2 becomes 22. So now the algorithm gets only these 3 values, 5, 407 and 22. So now if it has to select only one solution, it will select the first solution of 5, which is what I wanted the algorithm to do, because that is a feasible solution. Any doubt over here? I mean, usually for most slides I had question, but this violation seems to be kind of creating problem. Looks like violation is something that you people are not able to digest. Any doubt in this? Okay. Fine. So this slide might be a little bit complex, but then there is an immediate example, so we'll get it sorted out. So this is my problem. This is the problem that you are getting. Minimize f of x subject to g of x is less than g of x is greater than or equal to b. Right? I have j such constraints, not one constraint. There are many constraints, and I have I decision variables. Right? So first thing what I will do is I will normalize my constraint. So what I will do is I will do gj of x by b minus 1 is greater than or equal to 0. So each of the constraint I will normalize it. After normalizing, I will say given a solution, I will see whether if it is less than 0 or not. So the requirement is it has to be greater than or equal to 0. So if it is greater than or equal to 0, I am not going to assign any penalty. Right? This is my penalty. This is how I am calculating my penalty. So if it is greater than 0, I am not going to add penalty. So more like x1 square plus x2 square by 5 minus 1 should be greater than or equal to 0. So if I get a solution which satisfies this, right, that's what I am checking, right, this part. So if it is greater than or equal to 0, then I have no penalty. Else, whatever value I get, so this is greater than 0, greater than or equal to 0. So if it is 10 greater than or equal to 0, then no penalty. But if it is minus 5 greater than or equal to 0, then I have a penalty of 5. So the penalty value is absolute of this value. So that is how I am going to calculate penalty for each of the constraint, right? Not only one constraint. For each penalty, I will calculate, for each constraint, I will calculate what is the penalty, and then I will add all the penalties. So here I am just adding all the penalties. So for first constraint, how much is the violation? Second constraint, how much is the violation? That is what I am calculating over here. And over here, I am adding all the penalties, right? Here I am calculating the fitness function. So this is the fitness function equal to the objective function, which is given over here, right? Plus whatever we had lambda in the previous slide, that is nothing but Rm, right, into the total penalty. Total penalty is this omega x. Let's look at a problem and then again we'll come back to that. So this is my problem. Minimize f of x is equal to 1 plus x2 by x1. And I have two constraints. 9x1 plus x2 should be greater than or equal to 6. And 9x1 minus x2 should be greater than or equal to 1. And x1 should be between 0 and 0.1 and 1. And x2 should be between 0 and 5. So this is my problem. Right. So first what I will do is I will normalize my constraint. So 9x1 plus x2 by 6 minus 1 is greater than or equal to 0. And here I have 9x1 minus x2 minus 1 greater than or equal to 0. So both the constraint I have taken into this form, that the right hand side is greater than or equal to 0. Right. Then what I am going to do is, let's say I have these 6 solutions, S1 to S6, right? And for those 6 solutions, let's say the decision variable are this 0.31, 0.89, 0.38, 2.73, and like that for all the solutions. So once the decision variables are given, I can calculate the objective function. Objective function is nothing but 1 plus x2 by x1. So 1 plus 0.89 by 0.31 will give me 6.10. So 6.10, 9.82, 7.09, 7.85, 8.48, and 7.74. So which one has the best objective function value? It is this solution, 6.10. Right? But 6.10 does not satisfy the constraint. Right? So now what I will do is I am going to calculate what is 9x1 plus x2 by 6 minus 1 for each of the solution. So each of the solution, if I calculate, this solution, this solution, this solution actually have violations. Right? They do not satisfy. So is it clear now how I am getting this violation, how this 0.39 is coming? If you tell me no, then I can tell you exactly how it is. Okay. It seems everyone. Sorry. So
Sir,
the
please
question
can
is,
you repeat?
how did I get this 0.39? So this 6.10 is clear that I substitute the value of 0.31 and 0.89 in this function. So I will get 6.10. So that is not an issue. The question is, how did I get this 0.39?
So you substituted in the constraint equation,
Right.
and
So this x1 and x2 value, I will substitute in this equation, 9x1 plus x2 by 6 minus 1. If I do, it actually comes out to be minus 0.39. You can go back and calculate. It will come as minus 0.39. So the question is minus 0.39 greater than or equal to 0? The answer is no. So here it does not go over here. It is coming a negative value. Since it's coming a negative value, my violation is absolute of that value. So the absolute of minus 0.39 is 0.39. So this is the violation of the first solution due to not satisfying the first constraint. Right? Similarly, this 0.58, if 0.31, if you see the second solution, so 9 into x1, second solution 0.38 minus 2.73 minus 1 greater than or equal to 0. This, if you calculate, it will come as minus 0.31. Right? Since minus 0.31 is not greater than or equal to 0, I need to assign a penalty. What would be the penalty? The penalty is the absolute value of it. So I get this 0.31. Is it clear?
Yes, sir. No, it's clear.
Okay. So this is the penalty. This is omega 2, right? Omega 1 and omega 2. So violation in constraint 1 and violation in constraint 2. So what is my total penalty? Total penalty is nothing but sum of each of them. 0.39 plus 0, 0 plus 0.31, 0.58 plus 0, 0 plus 0, 0 plus 0, 0 plus 0. Right? So this is my total penalty. And I am taking a RM value of 20 over here. Right? So 20 plus omega into F. Right? So 6.10 plus 20 into 0.39. Because of this relation. So my F value, fitness, is the objective function value, which is here, plus RM, which is 20. I have taken it as 20, into total penalty. Total penalty is 0.39 plus 0.00. So this comes out to be 0.39. And this, if you calculate, comes out to be 13.90. So this is the fitness function. So now the algorithm gets only the fitness function. So if the algorithm has to select a solution, it will first select this solution, 7.74. Right? And that is what you want to happen, because 7.74 is a feasible solution. It has no violation. Right? Whereas 6.10 is definitely good in terms of objective function, but it has violation. It does not satisfy the constraint. Right? So the algorithm will work with this. So all those, if you are going to select the best solution, you are going to do something with the best solution, then it will select the sixth solution as the best solution. Is it clear? So
Yes, sir.
this is
Yes, sir.
something that you can pretty much use in all the algorithms which will be taught as part of this entire course. Right? Most likely all of them would stop with how to solve an unconstrained optimization problem using ant colony optimization, unconstrained optimization. How do you solve an unconstrained problem using TLBO? Because that itself is 1 hour, 2 hour material. So they may not necessarily be looking into constraint. So what do you do is take their technique. As soon as you get a solution, you see whether it is satisfying the constraints or not. If it is satisfying the constraints, well and good. If it is not satisfying the constraint, you need to calculate the fitness, right? And return back the fitness to the algorithm. The working of the algorithm is as such. For a constraint problem and unconstrained problem, it can be same thing. So whether I am solving this particular problem or this particular problem, the algorithm will not change. What will change is what I am returning to the algorithm. Once it gives decision variable, whether I am giving an objective function alone or whether I am giving the fitness function value. So fitness function value, if you have to give, then you need to have constraints. So objective function plus lambda times penalty, right? The penalty will be 0 for a feasible solution. So for a feasible solution, fitness function is nothing but your objective function. But for infeasible solution, you will incur penalty. And because of that penalty and this RM value, the value goes up. So now here, if you see, the objective function was good, 6.10. So this is like a student who has scored 439. This is like a student who has exactly scored 200, 40 marks in each subject, 5. So 200, right? Even then, this student has to be selected because the requirement is that every subject has to be passed, right? That is done by this fitness function. So if you have any doubts, we can discuss. Okay, let me see. So this is the same problem, 1 plus x2 by x1. So that is normalized, and then these constraints are plotted, right? And initially we start with 5 solutions. So this 1, 2, 3, 4, and 5 solutions. So there is one solution over here. 1, 2, 3, 4, 5. So those 5 solutions I have. So initially all those 5 solutions are in infeasible space. How did I identify infeasible space? I drew this line. I drew this line. I took a random point on one side, and I checked whether that point is feasible or infeasible. So like that, I identified this infeasible region. Now the algorithm does not know that there are these constraints. So for this problem, this animation which you are going to see is solved by TLBO. So TLBO probably will look at it tomorrow. So there, if you see, it is only calculating the fitness function and returning. So TLBO, when it tries to solve this problem, what it does actually is something that you can see here. So initially, if you see, the points are in the infeasible region. So as you can see, the points are moving into the feasible region. Right? All the 5 points have now kind of are in the borderline on the infeasible feasibility. Now many solutions have become feasible. Right? Now all solutions have become feasible. And for this problem, that is the optimal solution. That x1 is 1 and x2 is 0 is the optimal solution for this. So all the points are able to reach this particular solution. So this is x1, this is x2. Right? So this only shows how the variables are moving in the search space. So working of TLBO will be as exactly similar as what will be explained tomorrow. Only thing what we have done is we have taken that algorithm, we have implemented fitness function, and then we have just plotted to see how the algorithm is actually working. So any doubt over there? So apart from this, whatever has been covered, apart from that, if you have any doubt, I have 5-10 minutes still left. So if you have any doubt, we can discuss that.
So can we convert multi-objective function into single objective function by using any of the function?
So what is usually done is, just 1 second. So if you give me this problem, minimize the F1 and minimize F2, right? And let us say both of this objective function are conflicting. I am intentionally not writing max and min because very often that is the notion that one function is maximized, the other function is minimized. That means it is conflicting. That is not the case. Both functions can be minimization and still they could be conflicting. So minimize F1, minimize F2. So if you give me this, so I would say that I do not know how to solve this problem, right? So what I will do is I will say minimize capital F, which is equal to WF1 plus W2F2.
Okay,
right? And I will make this table. Sorry?
Yeah, using weightage, giving the weightage to the
So weighting function, I will not solve for one set of W1, W2. So what I will do is 0.1, 0.9, 0.2, 0.8, 0.3, 0.7. Like this, I will do lot of combinations.
Okay,
right?
sir. Thank you.
Okay. So any other doubt?
There are genetic algorithms and like swarm intelligence algorithms like good for multi-objective optimization problems, or
so that depends upon whom you are talking to. So there are people, so for example, someone who developed TLBO will say that TLBO is better than GA. They would have shown it on some problems. You go to someone who has developed GA, they will tell, no, TLBO is not working as it has been claimed. GA is a better algorithm than TLBO. So there is no end to that fight. Honestly, if you ask me, it is not possible to say that this algorithm is better than that algorithm for an arbitrary problem, right? But if you tell me I have a linear programming problem, and if you tell me will I use GA, I will say no, I will not use GA. Will I use TLBO? No, I will not use TLBO. Will I use PSO? I will not use PSO, because for linear programming, I have one nice algorithm which is called a simplex method. None of this algorithm will give guarantee, right? The ability to find and the guarantee, both are different thing, right? So simplex method comes with the guarantee that once the method is over, you have actually the solution that is the best possible solution. There is no better solution than that. Similarly, if I have an MILP, I will never use any of these techniques. I will use branch and bound. Now the question is, if I have nonlinear programming problem, an arbitrary nonlinear programming problem, again, nonlinear programming problem, you can classify as quadratic programming, looking at the function, whether the problem is convex or not convex. So again, you have special algorithm for that. But given just any arbitrary nonlinear programming problem, if you tell me, then there are mathematical programming techniques, and there are this GA, TLBO, all of those. What I put in I club them together as meta-heuristic techniques. Right? In that case, neither these guarantee nor these guarantee. Right? Even in those cases, I would first prefer to solve by mathematical programming techniques. It is not that I will go with meta-heuristic techniques. Meta-heuristic techniques are more useful when you do not have the problem in a required format. So all this mathematical programming techniques, simplex method, branch and bound, this mathematical programming techniques, problem is of this form. Maximize f of x subject to g of x is less than equal to 0, h of x is equal to 0. Right? Now if you tell me one constraint like this, that variable x1 should not be equal to variable x2. Is this a constraint? Yes, this is a constraint, but this constraint is not of this form. Right? So if I want to use mathematical programming techniques, I need to convert this constraint, right, into this form. If I'm able to convert this constraint into this form, then I will use mathematical programming techniques, because mathematical programming techniques require that the problem should be in this format. So in the next lecture, one of my student would show you mathematical programming technique based solvers. He's not going to explain the technique, how the technique is working, that he is not going to explain. He is going to explain, if you have MATLAB and if you have such a problem, how do you solve it? That's what he is going to explain. So there you will see that all your problems need to be of this form. Right? If this is not of this form, you cannot use mathematical programming techniques. Whereas in meta-heuristic techniques, it does not require your problem to be of this form. If it is of this form, yes, it can solve. But it is not hard and fast that your problem should be of this form. Right? So for example, very often you would see that you don't have a mathematical model of whatever you're trying to optimize. You have a more of a simulation. Right? So let's say I want to find out what is the best temperature and pressure, but I don't have a model. But if you tell me temperature and pressure, I can go and do an experiment. I can measure whatever I want. Let's say I want to measure concentration, conversion. So I will do that experiment and come and tell you what is the conversion. So those type of optimization problems are very common, wherein you don't have a mathematical model. So in that case, you cannot even use mathematical programming techniques. You will have to go with meta-heuristic techniques. Coming back to the question which you started is, people when they teach, if they are working from this domain, they will tell you that multi-objective optimization, meta-heuristic technique is best. That is not true. You can actually look into other books, classical optimization books, wherein, as I now said, if you have multi-objective optimization, you can convert it into a single objective optimization and solve. The usual criticism that they give is, there you will have to solve 10 times. So for example, 0.9, 0.1, 0.2, 0.8, that combination you will have to solve, let's say 10 times. They will say here you will get it in one time in genetic algorithm. That is also not true, because any of this algorithm, meta-heuristic algorithm, you will have to run multiple times. Only then you can be confident that whatever your solution you have got is the best solution, because all of them are based on random numbers. And if you change your random numbers, if you start from a different point, you will converge at a different point. So usually these algorithms, when you run from a large number of independent runs. Right? So it's not fully correct, but I won't be surprised if in this course itself you are given that statement that genetic algorithm is the best for multi-objective optimization. Very often people do that.
Okay, thank you, sir. So so you had mentioned that case where you can perform an experiment and get and then get an output instead of having a perfect mathematical model of the situation. So are objective functions sometimes modeled that way, as in a certain part of them is deterministic, but a certain part of them is non-deterministic?
Even that can be accommodated. Or let us say, so just think about any algorithm. Maybe tomorrow since TLBOE will be done, you will be able to you will be able to understand much easily. So for example, any algorithm if you take, it only gives me that the value of decision variable is x1, x2, x3. And then I am supposed to calculate what is the objective function value and return. Right? So now you are thinking about online thing. Right? Let us say I will say that you give me initial population. So initial population, it will give me, let's say temperature is 20, pressure is, let's say 2, 30, 1.8, 50, 3.5. So I will go and do this experiment, these 3 experiments, and I will come back and tell the algorithm this one gave me 0.8, this one gave me 0.75, this one gave me 0.96. So now the algorithm will still able to work with this solution and this one. It will not be real time. So what probably, if I understood your question correctly, it comes down to how is that I do an experiment and come back and tell to the algorithm, right? You can.
Yes, sir. Kind.
You got it?
Yes, sir. Like that is what I was kind of asking. Like, how do you?
So what I will do is I will take these values, perform an experiment, come and tell 0.8, and then the algorithm will work with these two solutions. So for that solution, I will again go and do an experiment and come back with an F value. Right? It is not necessary for me to have a mathematical model with respect to meta-heuristic techniques.
Okay. Okay, sir. Thank you.
If you want, you can drop. You will be able to get my email ID. You can drop me an email. Maybe we'll share papers with you wherein people have done like that. So I don't have a mathematical model, but I will go and run some other simulation, some other signal processing software. I will run. I will find out the fitness function and feed into this algorithm.
Okay. Okay, sir. Sure, sir. I'll email you.
Okay.
Right. Thank you.
Since there are some questions here.
Thank you, sir. Thank you very much.
Okay. So I think so some of these questions are kind of over. So anyway, since it is 5 o'clock, I will stop here. What we will do is we'll take a 10-15 minutes break. And then when you come back, I have 2 very good PhD students. So they will be actually showing you. I'll hang around. If there is some issue, I will be able to show it. Right now, I do not have MATLAB installed with me. So that's why I am kind of depending upon them. But those slides we have done multiple times. So I have been through it. So I don't think so you will have a problem. For whatever questions you have not been able to get satisfactory answer, you can just drop me an email and then we'll try to get back to you.
Thank you, sir. So shall we start at 5:15?
Yeah, we can start at 5:15.
Okay, okay. Okay, sir.
Thank you.
Hello, ma'am.
Yeah, hello, sir. Shall we start, sir?
Yeah, can
Yeah,
we
yeah.
start?
Yes, we can start, sir.
Okay.
So I welcome Prakash sir's scholars. They are going to demonstrate how to use the MATLAB optimization toolbox. I welcome both of you. Please go ahead.
Okay, ma'am. Hello, everyone. So welcome to today's hands-on session on MATLAB optimization solvers. So here we'll learn about the various inbuilt functions available in MATLAB to solve different category problems, such as linear programming, non-linear programming, integer linear programming, mixed integer linear programming, mixed integer non-linear programming. So as Sir has already told about the types of decision variables, types of objective function, and the types of constraints for this type of problems. So I will skip this part. So other than MATLAB software, there are two other different softwares as well, like IBM iLog Simplex, which can solve linear programming, mixed integer linear programming, and constraint programming. And there is GAMS also, in which we can solve LP, MILP, NLP, and MINLP problems. And using MATLAB optimization toolbox, we can solve LP, MILP, NLP, and MINLP. Okay. So in this session, we'll mainly cover the MATLAB optimization toolbox. So first, there are a lot of functions available in the MATLAB toolbox, such as linprop, which solves basically linear programming. In linprop, this basically solves MILT problems. Quadprop, quadratic programming. FMIN-UNC, that is non-linear optimization problem. Okay, but it is unconstrained. FMIN search, this also solves non-linear problem, but unconstrained one. FMIN-CON, it can solve non-linear problems, but with constrained equations. And we have pattern search, particles form optimization, simulated annealing bound, and genetic algorithm. These are like meta-heuristic techniques which can solve nonlinear problems. And there is only one inbuilt function, that is GA in MATLAB, which can solve mixed integer nonlinear problems. So we'll cover one by one. So first, for linear programming, the objective function should be linear, and it should have linear equality and linear inequality constraints. Similarly, we should have the bounds on the decision variables. So the inbuilt function available for linear programming in MATLAB is linprop. So we have this problem given. So the problem states like minimize Z, this one, subjected to the conditions. Okay, and the decision variables are greater than or equal to 0. So how to solve this problem using linprop? So the linprop inbuilt functions has certain input format which accepts the problem statements. So here you can see, so minimize F transpose X such that AX is less than or equal to B, A equal to X equal to B equal to, and LB less than or equal to X less than or equal to upper bound UB. So the A should be, the constraint should be written in a matrix form such that it is less than or equal to B. So for this problem, you can see that this is greater than or equal to inequality. So to use linprog, we must use this less than or equal to inequality. So before using linprog, you have to convert these equations into the appropriate format. So to get this appropriate format, we have to first multiply both sides of the equations by minus sign. This will give you the required format for linprog. So the calling syntax for linprog is shown here. Okay, so here for linprog, the first input is Z. So Z is nothing but the cost coefficients of the objective function, like 15, 10, and 20. And A is the inequality coefficient matrix A. So in this case, we the A is nothing but 2 cross 3 matrix. So with first row minus 0.1, minus 0.2, minus 0.4, which corresponds to the first constraint, and the second constraint corresponds to the second equation. So minus 0.45, minus 0.25, and minus 0.3. So this A is nothing. This is the inequality coefficient matrix, and the right side hand vector of the inequality constraint is B is minus 30 and minus 40. So, and the lower bounds is 0, because in this problem it is given that x1, x2, x3 should be greater than or equal to 0. So lower bound is 0, 0, 0 for x1, x2, x3, and the upper bound is like infinity. Okay, so next I will show you how to call this function in MATLAB. And this linprog will give you this output: x, fval, exit flag, output lambda. So x is nothing but the solution, the optimum solution vector, and fval is the function value at that optimum solution, and exit flag why the algorithm stopped, and output some informations regarding the iteration the algorithm used, such as those, and lambda the Lagrange multipliers. So to call this function in MATLAB, first we have to create a script file. So in MATLAB, you can create a script file by just clicking new script. And so I can just copy this code. So first, oops. So just save it as LP linear programming problem. So first line just clears the workspace, clears the command windows, this one, and clear will clear the all variables in the workspace here. So if you run this everything, every variables will be get cleared. And you need to define the lower bounds. So zeros, 1, 3. This is the inval function in MATLAB, zeros. It will define 1, 3 matrix, which with all the values 0. So this is the lower bound. And A, this is the inequality coefficient matrix, which I already told you. So you can define like this. So this is the first element up to until this semicolon. This is the first row. So if you put semicolon, that means you are moving to the next row, and space means you are moving to the next column. This is how you define the matrix A. Similarly, B you can define like this. Since B is a column vector, you can use transpose using apostrophe, and Z can be defined something like this. Now you can call the linprop using this calling syntax. So if I run this using run, you can see the output. So for this problem, we have optimal solution is the x1 value is 7.6923, x2 is 146.1538, and x3 is 0. The function value for this solution is 1.576 into 10 to the power 3, and exit flag is 1. That means the algorithm converts to the optimum solution, and some output information. Any doubt on this?
No, sir.
Okay. Yes. Yes, please. Okay. No. So next, we can solve the similar problems, but this problem has equality constraints. Okay. So how to solve this problem? This problem has inequality constraints as well as equality constraints, and we have bounds, different bounds on the decision variables. So we can call this. So we can again make a new script file, copy this code. Okay. So here, this Z is the coefficient matrix of this probe. Here, 1, 2, minus 3. And A is the inequality matrix. This inequality concept 1, 2, 0, and 0, 1, 1. So this is defined. Similarly, right hand side vector B is defined as 3, 2. So 3, 2. Now for equality constraint, you have to define another coefficient matrix, A equality. So it consists only one equation. So this one, all the coefficients are 1, 1, 1, and the right hand side value is 4. See, the lower bound for the x1 is 0, the x2 is minus 1.5, and x3 is 0. The upper bound for x1 is 5, x2 is 3, and x3 is 2. Okay, so if I call this function, so I will get the optimum solution like this with the function value minus 5.5. Okay, so any doubt?
Sir, please show the previous screen once more, the programming part.
Okay, this one.
Yes, thank you, sir.
Any doubt on this?
No.
So if you want to learn more about this inbuilt function, linprog, then you can type help linprog in the command window, then just enter. So here it will explain everything about this inbuilt function. So this is the format, like linprog f a comma b attempts to solve the linear programming problem. Does that minimize f transpose star x subject to this inequality? Similarly, a equality and b equality are the linear equality constraints. So you can read about it. And similarly, the exit flag, like exit flag equal to 1 means converge to the solution x. Similarly, you can also click doc linprog. So here also you can read about the linprog in detail. Also, some examples are given, so you can follow this. Okay. Any doubt? Okay, so we'll move to the next. So mixed integer linear programming. So for mixed integer linear programming, the objective function should be linear. We should have linear equality and inequality constraints and bounds on the decision variables, as well as it can consist of integer variables. So the inbuilt function in MATLAB is int_lin_prog. Okay. So let's solve this problem. So our objective is to maximize profit, z equal to 5x1 plus 4x2, subjected to this constraints. This is basically linear inequality constraint, and this also. So here equality constraints are not there. So how to formulate this and solve using int_lin_prog. And here both the decision variables x1 and x2 are integers, because x1 says like units of exterior paint produced. Okay, so this int_lin_prog basically requires this format. So ax less than equal to b, this linear inequality constraint, and we have linear equality constraint and the bounds. And along with this, we have incon. You have to say that which decision variables are integers. So that it can be specified using the this index of the factor. Okay, so how to solve this problem? So for this int_lin_prog, it takes the z as input, first input. So here z is this.
মা আমার রাতে রুটি করি।
Am I audible?
Yes,
You
sir.
are audible.
Yes, sir. Yes, sir. You are audible. Please go ahead, sir.
Okay. This int_lin_prog assumes the format minimize the objective function. So since for our problem it is maximization case, so you have to use minus. Since maximize z is same as minimize minus z, so we can use z is equal to -5 -4. Okay, so similarly we can define the inequality matrix and constant vector b. So this has to be in the less than equal to format. Since yes, this one x2 less than equal to x1 plus 1 was in different format, so you have to rearrange this so that we can use this. Okay, similarly the bounds are given x1 x2 greater than equal to 0 and x2 is less than equal to 2. Okay, so these are given. So how to run this? So first, create a script file. Paste. So if you run this, you'll get this solution. The optimum solution 4, 4 and 0. Then optimum function value minus 20. So for our case, it should be 20 since it is maximization. So in this calling function, this square bracket means the equality constraints are missing. So here a equality is missing, so you should put square brackets. That means empty vector. Here also the equality right hand side vector is empty, so you have to put square brackets. And the incon, this is important because you have to tell the algorithm which decision variables are integers. In this case, it is referred as 1 and 2. That means both x1 and x2 are integers. You can also change, let's say you only x1 is integer, then you just change this to 1 only. If only x2 is integer, then you can say like this. Okay. Next, we move to constrained nonlinear programming. So in constrained nonlinear programming, the objective function should be, it can be linear or nonlinear, and the equality constraints and inequality constraints can be linear and nonlinear, and the bounds on the decision variables should be given. So for this type of problems, we have fmin-con, GA, genetic algorithm, and pattern search. These are the inbuilt functions available in MATLAB. So this is the problem. So minimize fx such that x1 plus x2 and x3. This is the objective function subjected to the conditions here. All are linear inequalities. Some are linear inequalities and some are nonlinear equalities. Okay, so and the bounds on the decision variables are also given. So how to solve this using fmin-con? So this is the syntax for fmin-con. It takes input the function for the objective function x0. X0 is the initial guess value. A is the inequality linear inequality matrix. B is the right hand side vector of the linear inequality, and A equality is the linear equality. Similarly, B equality is the right hand side vector, and LB is the lower bound, UB is the upper bound of the decision variables. Non-LCON is the non-linear constraints. It involves both the equality as well as inequality constraints. So this is the format the fmin-con asks. So minimize fx is that the non-linear inequality is less than 0. The equality means the non-linear equality should be equal to 0. This is the linear inequality. This is linear equality, and these are the bounds. So to solve this problem, first we have to define the objective function. So So this is the objective function. It takes the input x. X is the solution vector. So, and since the objective function value is equal to x1 plus x2 equal to x plus x3, so we can simply calculate using sum annual function. So from x1 to 3. So you can save this function. Next, we have to create a function file, nlcon, which takes into account the nonlinear inequalities and the nonlinear equalities. So you have to create this function. So this nlcon function will take the input x, which is a vector. So the first nonlinear inequality equation, the value will be calculated. So this is the equation, first equation. This is second equation, and this is third equation. So accordingly, it has been calculated. So x in parenthesis 1 means it is x1. X in parenthesis 6 means it is the x6. And in this problem, we don't have the nonlinear inequality, nonlinear equality constraint. So it is left as blank, so empty. So this function should return you this c value and c equality value. And this c is a vector. Next, since we have this linear inequalities as well, these linear inequalities should be provided as in the matrix form, ax less than equal to b. So you have to define the matrix A. So the first row corresponds to the first equation. So you can see that first three columns are 0, 0. Because x1, x2, x3 are 0, coefficients of x1, x2, x3 are 0 in the first equation. The coefficient of x4 is 0.0025. Similarly, the coefficient of the x6 in this equation is 0.0025, and rest are 0. Similarly, you can write the other two equations. And the right-hand side vector b is, it can be written as 1, 1, 1. So you can call this fmincon using this script file. So if you so here everything is defined. The right-hand side vector v, which are all ones, lower bounds defined. Since we have 8 decision variables, so first 3 decision variables, x1, x2, x3, lower bound values are 100, 1000, 1000, and the rest of the 5 decision variables are the 10, 10, 10. So basically, once 1,5 will create the this row vector 1, 1, 1, and multiplied with 10 will give you the 10, 10, 10. So similarly, you can create the upper bound. So here for fmincon, you need to give the initial guess x0. So in this case, it is taken as the lower bound, but you can also choose other values or something like average values, LB plus UB by 2. And this fun will, it's the function handle for the objective function here. You can also directly copy this and paste instead of function here. It will also work the same. So, and the non-linear con is also function handle for the non-linear constraints function file. So if you call this, so you will get the optimum solution, something like this. The function value, optimum function value 7.049 into 10 to the power 3. Any doubt? Okay. So next we'll cover the genetic algorithm. So the inbuilt function is GA. So let's solve this problem. Maximize fx 1 plus x1 square plus x2 whole square and raised to the power minus 1. This is the objective function subjected to the non-linear inequality constraints. These two equations are non-linear, and we have one linear equality constraint, and the bounds are given. So how to solve this using GA? So the syntax for GA is, it first takes the function handle for the objective function nvar. Nvar will nvar is the like number of decision variables. In this case, it is 2. A is the coefficient matrix for this linear inequality. A equality is the coefficient matrix for the linear equality, and LB, UB, the lower and upper bounds. Non-LCON is the non-linear constraint function. INCON is the, if you have like integer decision variable, then you have to specify the index in this INCON. And options, you can change the default options of the genetic algorithm using options, which I will explain in the last. So using this syntax, you can solve this problem. The GA takes the input in certain format. So this all are same as previous fmin_con. Only you have x in con input in GA, which was missing in fmin_con. Similarly, this is also missing in the pattern search. So GA is the only inbuilt function which can solve mixed integer non-linear program. So to solve this problem, first we have to create the objective function file. We have to create the non-linear constraint function file, and we can specify the equality coefficient matrix. And since we don't have integer decision variables in this case, so in con we can put as blank. So first we'll define the function file. So this will create the objective function. Next we have to create the non-linear equations function file. So since we don't have this non-linear equality constraint, so this C equality is blank. So now we can call the genetic algorithm. So here you might see this RNG1 twister. Since the genetic algorithm is stochastic in nature, so we can fix the seed number for the algorithm so that you can reproduce the answer every time you run. So if you change the seed number to 2, the solution might be different. But if you fix the seed to 1 and run it several times, then you will get the same answer. So RNG is the inbuilt function for random number generator in MATLAB, which takes the seed number as the first input and the algorithm to generate the seed number, that is twister. So we'll fix this. Then this is the function handle for the objective function. As the problem consisted of the linear equality constraints, so we have defined the coefficients accordingly. Then we have the lower bounds and upper bounds for the decision variables, and number of decision variables n var is equal to 2, which is nothing but the size of the vector LV, that is 1 to 2. And we have the function handle for the nonlinear inequality constraint and as well as equality constraint. So now we can call the GA function. So you can see that the linear inequalities are missing in this problem. So you have to test blank square brackets. So now we can run this problem. So this will give the optimum solution 1.5 and minus 1.5, and the optimum function value is minus 0.1819. Any doubt? Okay, so we'll move to the next. So we have pattern search. So pattern search can also solve the nonlinear program problems. So it takes this syntax like this: minimize fx, subject it to the conditions, nonlinear inequalities, nonlinear equalities, linear inequalities, linear equalities, and the lower and upper bounds. So the main difference between the GA and pattern search is that pattern search cannot handle integer decision variables. Otherwise, it's all the same. So also we have to give the this one initial guess value x0 in pattern search. So if we want to solve the same problem, then we can copy this code and run. So here again, a pattern search is a random algorithm, stochastic algorithm. So you have to fix the seed number for reproducibility. Here we don't have any linear inequalities, so this is left as blank. You can call this. So the pattern search also gave the same solution for this problem. Next, we have simulated annealing and particle swarm. So we'll cover it at the end of the lecture if the time permits. Similarly, these are like nonlinear, unconstrained nonlinear programming. So we don't have to specify any constraints. We have two functions available in MATLAB, fmin unc and fmin search, which cannot handle the constraints. These are similar in nature, so I will come to this later. Quadratic programming also I will come to later. So how to solve the mixed integer nonlinear programming using MATLAB? So there is only one inbuilt function, that is GA in MATLAB, which can solve the mixed integer nonlinear programming. But there are certain restrictions to solve. So let's first solve this problem. So the objective function is minimize fxy, this one minus y plus 2x minus ln x by 2, subject to this non-linear inequalities constraint, and we have bounds. So x is bounded between 0.5 and 1.5, and y is an integer variable. It can take the value 0 or 1. So you can solve this problem using GA. So first we have to create the function file for the objective function. Next, you can create the nonlinear inequality function file. Again, we don't have the nonlinear equality constraints, so this equality is blank. Save this file. Next, we can call the GA. So here incon refers to the decision variable, which is integer. So in this case, x2 is the integer. So it is specified as 2. There. So, you can call this function file, script file, and the optimum solution is 1.374 and 1, and the function value is 2.1237. So there are certain restrictions using GA while solving the MINLP problems. So in earlier versions, you cannot have the linear equality as well as non-linear equality constraints if you have integer decision variables. But in the these newer versions, you can solve the MINLP problem if you have this linear equality constraints. But you cannot solve the MINLP problem if you have non-linear equality constraints. So same is depicted here. So if you have, this is the MNLP problem. You cannot solve this problem using GA because it has non-linear equality constraint and linear equality constraint. If you remove the non-linear equality constraint, you can solve this in newer versions but in older versions you cannot solve. And similarly, if you have only equality, yes. Yeah, you can also in problem. Yes, if you have non-linear equality constraint, then you cannot solve this. And if you don't have any non-linear equality and linear equality, then you can solve this using GA. If you don't have any integer variables, then you can solve with all the non-linear equality as well as inequality, and linear equality and inequality. So these are the syntax for calling the various functions discussed: linproc, int linproc, this fminCon, GA. So till now we solved all the till now we solved the problems using the default settings of the algorithms. If you want to change the default values used in the solvers, then you can use the optim options command. So I will demonstrate how to use this. So let's say we want to change the crossover probability in GA to 0.6, and we also want to include plot function, which plots the iteration versus the best objective function value. So to show this, we have to first let's define the objective function. So okay, so the GA syntax, at the end you can see options. So these options can be changed using optim options. So the options equal to optim options. So for first you have to say the algorithm name or solver name. In this case it is GA, and next we have something like name value pair. So plot function, what type of plot function we want to plot. So GA plot best, and the crossover fraction, what should be the value? 0.6. So we set the values like this. Also you can change, let's say, the maximum number of iterations. So you can use like max iterations, let's say 50, and also you can set the population size to 20. So this way you can change the default values of the algorithm. So you can run this. Your max. For this case, okay. So max, instead of max iterations, it should be max generations. So if you run this, you will get this plot as desired, and the crossover fraction is changed to 0.6. Maximum generation set to 50 and population size of 20. So there are a lot of this name value pairs for GA available. Like I'd say constraint tolerance. So the default values, you can change the default values of this by changing this value, constraint tolerance. Similarly, crossover fraction we did, and elite count, hybrid functions, function. What should be the function tolerance? You can change using these options. So there is a graphical user interface in MATLAB. So in older versions, it was Paulus Optim tool, but in newer version, it is not available. Instead, this live editor is available for the newer versions. So it's pretty easy to solve these problems using any solver. So let's solve one problem using this GUI or live script. So first you can set the type of problem. So objective. So in this problem, the objective is nonlinear. So you can select nonlinear. So it will be selected. And is it constrained? Okay. So for the constraints, what are the types of constraints available? So we have only one nonlinear inequality constraint. So you can select nonlinear. And what is the solver you want to use? You can select based on your the objective function type and the constraints. It will recommend you a solver. So this MATLAB toolbox has recommended us fmincon. Now we have to give the local function. So you can select from here, from file or from local function. This will do. So this was the function defined. So you can give it as an input. So we solved it using GA. So let's stick with GA. Number of variables was D. Constraints, we have nonlinear constraints. So it was defined as non-L on int. So you can browse it. Then you can choose final output, what you want to plot. You can choose best individual, best fitness. So here number of variables, it is taking D, but you can also select other values. So here you can define the D value. So in this case we have 2. So if you run this, okay, we because of the nonlinear values, these constraint equations are giving some imaginary values. That's why the error is coming. If you select other problems, it will give the good values. So basically, this is how you can use the live script to solve the optimization problem. Also, you can get the desired values from the algorithm, which the algorithm by itself doesn't give, using output functions. So, suppose you want to see the population after every iteration. So you can see that with the help of output function. So we can see how to use output function to get different solutions, otherwise which the algorithm doesn't give. So how to use output function? See, so using optim options, you can set this is solver name for which algorithm you want to change the output function. So here output function, and here you can define your own custom output function. So there are some rules for creating the output function. So this should be the syntax of the output function. State options op changed, and output function options is the input and state and like. So if op change options are changed, then op change is equal to 1, else it is 0. So next slide, you can see. So let's this function is already defined earlier, so we'll create a output function. So this is the function name is output function example. First, the options change is false because it is to indicate that the change in options. And then current population. So state contains, here the state is the input. The state contains the details about the population. So it is in structure form. So state.population will give you the current population. Now from this current pop, I will plot the first column versus second column. That means x1 versus x2. So this is the output function defined. Next, we'll call the GA. So here, if you can see, options is changed. So optim options, the solver is GA. The output function is changed to the output function example as defined earlier. And crossover fraction is changed to 0.6. So if you run this, so you will get this plot, which was defined in the output function example. The next, vectorization of the fitness function. So how to vectorize the objective function so that the speed of execution is increased. So for example, we have defined the same objective function in two different forms. The first one is the vectorized code, and the second one is the not unvectorized one. So in the second case, unvectorized code, so here the function takes x as a single solution as input, but in the vectorized one, x is basically a population. So it gives a row of solutions. Suppose you have 3 decision variables. So instead of 3 decision variables, instead of taking 1 cross 3 for this case, in the vectorized code, it can take any n cross 3 input. So for the unvectorized code, it accepts the vector x as 1 cross d, and after calculating the function value, it will return the objective function f as single scalar value. While the vectorized code can accept n cross d. So n can be any number of solutions, or basically it can accept a population. And the this vectorized code returns the objective function value in a column vector n cross 1. So let's see what is the importance of vectorized code versus unvectorized code. So we can create a simple script file to see how much time it is taking for a vectorized code and for an unvectorized code. So copy this code. So here, to calculate the execution time, there's a one inbuilt function TikTok. So TikTok will give you the time to run the code between these two, between tick and top, and the time will be saved in novec, this variable. Similarly, for vectorize code, it will be saved in vec variable. So this the first one calls the unvectorized code, the second one calls the vectorized one. So if you run this code, you can check the difference in time. Okay. Okay, this restringent vectorize was not defined earlier, so we have to define it. So you can see the difference in this times taken by the both vectorized and unvectorized formats. So the without vectorization will take you 7.02 seconds, and with vectorization it takes 5.89 seconds. So for large problems, you can significantly improve the time. Also, you can use the parallel processing so to improve the speed of execution. So the only problem is you cannot use the vectorized form while using parallel processing. So to start parallel processing, you have to set the options, which is this one: optimum option, solver name, use parallel true, and use vectorized false. So, and this parallel processing option is available for GA, particle swarm, and pattern search algorithm. So let's see what's so you can create objective function using this, and you can simulate an expensive function by using the pause function. The pause function will pause the execution for 0.01 seconds. So it is creating a costlier function. So, and to use parallel processing, you can use the parpool function. So here this first part doesn't use parallel processing, so we did not use parpool here. So this was run without parpool, and next we are going to use the parallel pool. So this part of the code was run using the parallel processing. So you can see the time difference between these two. So using parallel processing, it takes 853 seconds. And with parallel processing, it takes 123.61 seconds. So you can significantly improve the processing time using parallel processing. So next, multi-objective optimization. In MATLAB, we have two functions, GA multi-objective and Pareto search. Both can solve multi-objective problems. So the syntax for GA multi-object OBJ is like this, and which is similar as GA. So let's solve this problem. This is core multi-objective optimization problem. We have two objective functions, f1 and f2, and both are like minimize f1 and minimize f2. So we can solve this problem. So first, create the objective function file. So for multi-objective function file, you have to return the function value as a vector. So here f1, first element of the vector, corresponds to the objective function 1, and second element corresponds to the second objective function value. So we can call the GA multi-OBJ using the script file. For simplicity, we are ignoring the constraints here. So the GA multi-OBJ will return the optimum solution X. This will be in the Pareto front, non-dominated solutions. F-well is the objective function values corresponding to each solution. So if we run, so here you have got this Pareto front. This is optimal Pareto front, and since we have minimized f1, minimized f2, this Pareto front lies on the bottom left corner, as discussed in previous class. Any doubt? Similarly, we can call Pareto search to solve multi-objective problems. So you can just copy the script file. So just run it. It also gives the Pareto front as a solution, and the X is nothing but the solution corresponding to the Pareto optimal solutions. So we can cover the remaining functions. So go So we can cover the quad proc, fmin-unc, fmin search, and particle swarm and simulated annealing. So simulated annealing and particle swarm in MATLAB. These are the inbuilt functions: simul anneal BND particle swarm. This is the name of the algorithms. So these two functions cannot solve the constrained nonlinear problems. So we only have to give the nonlinear objective function and the bounds on the decision variables. It cannot handle integer decision variables, all the constraints. So let's solve this problem. So we have the objective function. This is called restringent function. Here is the graph for this function. As you can see, it's very complex function. So this restringent function is already defined. So we can call using this code. The structure, input structure for this simulated annealing is, it takes the function handle for the objective function x naught initial guess value for the decision variables and lower bound and upper bound, and it will return the optimal solution x, the optimal function value, and exit flag output. So it gave the optimal solution as this one, almost close to 0, and the objective function value also 0. Similarly, you can call the particle swarm. So the particle swarm takes the objective function as input. D is the number of decision variables, and LB and UB are the lower and upper bounds. So to solve the problem, it also gives similar values. So next we have this fmin-unc and fmin search. This solves the nonlinear problems without any constraints and nonlinear objective function only. So we have Rosenbrock's function defined as this, and the gradient is this. So how to call using fmin-unc? So first create the function file. So this is a function file. So here, this Rosenbrock with grad, it takes the input x and calculates the function value as well as the gradients. Now we can call the and this fmin ank doesn't have any bounds on decision variables as input. It only takes initial case value. So if you run this, it says local minimum found and the optimum solution is 1 1 and the function value is 0. Similarly, fmin search can be used. So fmin search doesn't need any gradient details. So this is a Rosenbrock without gradient function. Next we can call the function. So similar to fnum, it requires initial guess value x naught. If you run this, so the optimal solution is 1, 1 and the function value is 0. Next we have quadratic programming. So for quadratic programming, the objective function should be in quadratic form. The highest power should be 2. It should have linear equality and inequality constraints. It cannot handle nonlinear constraints, and it should have the bounds on the decision variables. The name for the inbuilt function is quadprog. So to solve this problem, you can see that this objective function is quadratic in nature. We have 2 decision variables, and we have linear constraints, linear inequality constraints, and we have bounds on the decision variables. So how to solve this using quadprog? So to solve this, the quadprog takes something like this. So H. So this H is the Hessian matrix. F is the objective function value. A is the linear inequality coefficient matrix. B is the linear equality right hand side vector. A equality, B equality, those are corresponds to the equality constraints, similar to linprog and intlinprog. And apart from that, you need to give the initial guess value x naught. And with options, you can also change the default settings of the quadprog. So to solve this problem, so first you have to define h. H is nothing but if you double differentiate, and you can get this matrix, so which is nothing but 2 minus 2 minus 2 comma 4. And what is f? F is nothing but the coefficients of the decision variables with order 1. So minus 4 is the coefficient of x1 minus 4, and here x2 is not there present, so it is 0. Similarly, the a b is defined, and lb lower bound is 0 0, up is infinity, so we can skip that. The algorithm will automatically take the upper bounds, and we don't have linear equality constraints here, so a equality and b equality can be skipped or provided as a blank vector. So to solve this problem, we can create a script file. You can see the upper bound is defined as null. So if you run this, it says minimum found. So the optimal solution is 2.4615, 1.079. The function value is minus 6.769. So we have covered linproc, intlinproc, quadproc, fmin, fmin search, simulated annealing, bound, particle swarm, fmin-con, pattern search, and GA. And also the multi-objective functions using GA and Pareto search. So till now, any doubt? Any doubt on this? Any questions?
Hello.
Yes.
Is there any simulation tool for this optimization? You are just you are showing the codes in the editor window. Is there any simulation option available in MATLAB, a simulation tool for the optimization?
You mean like graphical
Yeah.
user?
Yes, like all we have for the power electronics, we have the sim power system. So
Okay.
all the blocks are there. So for like that, do MATLAB has some like for optimization?
Yes. In earlier versions, we had this one Optim tool. This is optimization toolbox.
Okay.
So if you enter Optim tool, or also you can find out here like this apps in optimization. Can you see this?
Okay.
If you enter Optim tool, then in newer versions it is discarded, so you can use this live editor. This is also very user friendly. You can solve the problems using this live editor. Let's say like this, you have what type of objective function you have, what type of constraints you have,
Okay.
like that. Okay.
Thank you.
Any questions? Also, you can search all these inbuilt functions in the documentation also. So if you type DOC and the solver name, it's linprog, then it shows you the details about that algorithm. Also, it has solved some examples. You can go through it and learn how to solve it. And here also you can see optimization toolbox, and you can read about optimization toolbox, how to get started, how to solve problems, how to solve nonlinear optimization. You can go through all this to learn more. Okay. So if there is no doubt, then we can conclude the session. Thank you for joining this session.
Thank you.